let's take a look at the homework that we had last night on page 467, questions number 1 to 13. What issues did we have with 467, 1 to 13? Just let me know if you have a question with any of them. 7? Is that it? Did I hear number 6? Did I hear someone say 6? 6? Okay, so we'll go 6 and 7. 6 is a qualitative one, a good qualitative one. 7 is a quantitative one based on the graph, which is a good one to go over as well. 6 says, using the concept of impulse, explain how a karate expert can break a board. Does anybody do karate here? Anybody ever broke a board with their hand? I had somebody 2 years ago. I asked that same question 2 years ago, and a girl puts up her hand and says, "Yeah, I do karate, or jiu-jitsu, or something like that." And I said, "Can you break a board?" And she said, "Yeah." I said, "Can you show us?" She said, "Yeah." I said, "Well, so you can bring in a board tomorrow or whatever?" She said, "No, actually, I have a couple boards in art." So she went up and got these boards, and she had 2 guys hold these boards like at about neck height, and she didn't break it with her hand. She kicked it with her foot and broke this board with her foot at neck height. And I'm like, I can't even get my foot that high, let alone break a board when it's that high. Does anybody know the answer to this question using the concept of impulse? Explain how a karate expert can break a board. Ultimately, you want to maximize the force on the board, right? This is kind of the opposite of what we were talking about yesterday. What did we say yesterday? Typically, we want to minimize the force, right? When you have an impact cushioning device like a helmet or like a baseball glove or an airbag in a car or anything that's designed to cushion an impact, you want to minimize the force. Here we don't want to minimize the force, we want to maximize the force in order to break this board. How do we maximize the force? Well, first of all, let's give it as much impulse as we can. How do we give it impulse? Well, let's put our weight into it. Let's get our hand moving fast so that it has a lot of momentum when it hits the board. After it's done, it's going to have 0 momentum, your hand. Let's give it as much impulse as we can. Then, let's make sure it stops in as short of a time as possible. So you're going to hit it quick so that if you minimize the time, what do you end up doing to the force? It increases the force, right? The airbag increases the time and decreases the force. Here we want to decrease the time to therefore increase the force. So it's the exact opposite of some kind of impact cushioning safety device. Does that make sense? It's a good application of what we've been doing here. Question number 7, right away, I'm not even going to read the question right away. I'm just going to look at the question from afar and say 3 words. What are those 3 words? Area equals impulse. Okay, area equals impulse. Whenever we see that graph, force versus time, we think area equals impulse. Now, I am going to circle one little thing on the x-axis here because I spotted that that's in milliseconds, not in seconds. When we're doing a calculation, we've got to make sure that we multiply that by 10 to the minus 3 in order to get the time in seconds, which is what we want. Now, let's read the question and see exactly what we're asked for here. From the graph below, what is the magnitude of the impulse provided to a 48-gram, and again, a non-standard set of units here, tennis ball that is served due south? Well, we know that area is equal to impulse, so let's calculate the area of this, which of course is going to give us the impulse. It's a triangle, so when we calculate the area of this, we're just going to use 1/2 base times height. Now, some people, I've done this before as well, say like, oh, you got to break that up into 2 triangles, 1/2 base times height, and then add it to 1/2 base times height again. Do we need to do that? No, not at all. Okay, I've done that just because I wasn't thinking real well. In the end, it works. It's still correct, but we don't need to do that because we don't need a right-angled triangle to use the equation 1/2 base times height. The base of this, it goes from 0.5 up to 5.5, so the base of it is going to be 5 times 10 to the minus 3. Don't forget the exponent. The height of it is 900. So we're going to say the area, or the impulse, is equal to 2.5 times 10 to the minus 3. That's 1/2 of 5 times 900, which is going to give us, what is that? 2.25 times 10 to the negative 1. Is that right? Somebody have that calculated? Just 2.25? Okay. 2.25, and the units for that, because it's impulse, would be Newton seconds or kilograms meters per second. So there's the answer to A, the impulse, 2.25 Newton seconds. Obviously, we're going to get a completely different answer in terms of the exponent if we forgot to make it 10 to the minus 3 for the base there. You got to figure if it's a multiple choice question too, you got to figure that one of the options is going to be what we would have gotten if we had forgot to put the 10 to the minus 3 there. All right, B says, what's the velocity of the ball when the racket and the ball separate? Let's assume that it starts from rest. When the ball is served, of course, it is starting from rest. So when we find the change in velocity, that's going to be the exact same value as the final velocity. Now, if we were given an initial velocity already that wasn't 0, then we'd find the change in velocity, set that equal to Vf minus Vi, and then we'd get final velocity that way. This one's a little bit easier because, again, we're just looking essentially for the change in velocity. The equation that we're going to use here is impulse is equal to m times delta V. And we're going to rearrange that to get delta V is equal to impulse over m. The impulse we already have, we just calculated it, 2.25 Newton seconds. And the mass is 0.048 kilograms. Or if you don't like moving the decimal place over, just say 48 times 10 to the minus 3 kilograms. What do we end up getting for the change in velocity here? 2.25 divided by 0.048. 46.875. We're going to round that. We'll round it to 2 digits here, 47 meters per second. So that is the change in velocity, but because the initial velocity was 0, it's also the final velocity. If the initial velocity was 10, what would the final velocity be? If it had started off at 10 meters per second, what would our final velocity be? If it changes 48, the final would be 58, right? If we start at 10 and we go up by 48, then the final velocity would be 58. Be prepared for something like that as well, just in case you're not actually asked for the change in velocity or you're not given an initial velocity of 0, but rather an initial velocity of something else. Okay. You've got to figure if it's a multiple choice question. Again, the initial velocity is 10. One of the options will still be for the final velocity 47, even though that's not the final velocity in that case. Any other questions on this? We're good with that? All right, I'm going to assign right now worksheet number 2, which a number of you either have finished or almost finished from working on Unscheduled Help the other day. So worksheet number 2, that is homework for tomorrow. If you've got it done already, that's great. If you don't have it done already, then let's get it done for tomorrow. What I'd like to do for the next couple of minutes right now is have you work on a couple of multiple choice questions. Then we'll go over those multiple choice questions if we need to. The first one that I want you to work on is in your worksheet booklet at the end of it, multiple choice question number 7. So take a look at that. It's up on the board. It's also in the back of your book. See what you can do with that for the next 2 minutes or so, and then we'll take a look at it as a class. So we got a question here that asks us for the impulse delivered by a hammer to a pile. Just so that you understand what's going on in this question, this is a context question that involves concepts that we've seen before, but context that we haven't seen before. A pile driver is literally something that's designed to drive a pile into the ground. That's it. You see these, we've seen a lot of that happening in the south end of Calgary, down by 130th or by 22X in the last couple of years. They have these big machines that look like cranes. They haul these big masses up into the air, and then they literally just drop them. They drop them onto these piles and drive these piles into the ground. What these piles are friction piles. They basically provide a foundation for heavy things. They put them into the ground when they're building a bridge so that the bridge has something sturdy to sit on, so that the bridge basically doesn't sink into the ground. And that's what they've been doing over the last couple of years at 22X there, and 22X in Deerfoot in Calgary. This pile driver lifts a 900 kilogram hammer a distance of 3.5 meters above the top of the pile and then allows it to drop. We want to find the magnitude of the impulse delivered by the hammer to the pile. So let's be real clear on what's happening here, okay? This hammer is falling, and then it's hitting a pile. We want to find the impulse of the hammer to the pile. So we're not so much analyzing the fall of the hammer here. We're analyzing when the hammer hits the pile. There's two real separate questions here. The hammer hitting the pile and the hammer falling. Two separate questions. Now, we may end up having to do both of them, but what we're actually looking for is the second part of it, where the hammer hits the pile. Does that make sense? All right, there's no non-standard units that we got to worry about here. That's a good thing. Okay, we've got a mass here, 900 kilograms. We've got the hammer falling 3.5 meters. Let's call that its displacement because it's falling 3.5 meters. And we want to find the impulse of the hammer delivered to the pile, delta P. Let's say delta P is equal to PF minus PI. It's equal to F times T. And it's also equal to M times delta V. Obviously, we're going to use this part of the equation since we're looking for impulse. Now, I don't see anything about a force in a time here. So in all likelihood, I'm probably going to use this part of the equation as well, M times delta V. So let's say the impulse is equal to M times delta V. In this case, 900 kilograms, the mass, times VF minus VI. Now, VF of this hammer after it hits the pile is what? How fast is this hammer moving after it hits the pile? Falls and hits the pile and stops. So the final velocity of this hammer is 0. What's the initial velocity of this hammer? Well, if you look at it, of the hammer. If you look at it way up here, it's 0. But that's a separate problem. We want to know the initial velocity right here. The initial velocity in this problem when the hammer hits the pile. What is that? Do we know how fast it's moving at that point? We don't. So let's get it. Let's get what VI is. Let's get what VI is by analyzing the fall of the hammer. For the fall of the hammer, we could say VF squared is equal to VI squared plus 2AD. VF for the fall ends up being VI for the collision. Does that make sense? The velocity that it's moving at the end of the fall is the same as the velocity that it's moving at the beginning of the collision. So VF for one problem becomes VI for the next problem. Let's solve for that VF. VI for the first problem, the hammer falling, is 0 because it starts at rest up there. 2 times neg 9.81 times the displacement of neg 3.5. Let's square root that. I'm not sure what we get there for the final speed. Anybody have that value? 8.2867 meters per second. We plug that in here, 8.2867 meters per second. Do the math on that one. I think we end up getting 7.46. 7.46 times 10 to the 3, right? I actually get a negative value. 7.46 times 10 to the 3 Newton seconds. Now, they're only asking me for the magnitude, and they're giving me the units in kilonewtons seconds. So if we drop the 10 to the 3 to give us kilonewtons, then we end up with 7.46. How many people got that one? Good, good. It's kind of a tough question, actually. It's kind of a tough question because of the way that it's phrased. In the end, we end up doing something that's pretty much like we've done a couple of times before, right? The whole VF squared thing equals VI squared and then something else at the end. We just got to recognize that that's what we got to do in a completely new context here. All right, next question, number 8. I'll have you do right now. It should go a little bit quicker for us because it is a bit more straightforward. See what you can do with that over the next 60 seconds or so, and then we'll take a look at it as a class. Let's take a look at question number 8 now. It says the impulse is delivered by the pile driver in 2.1 times 10 to the negative 3 seconds. The magnitude of the force the hammer exerts on the pile is what? Right away, I see a force, and I see a time, and that tells me what? Force and time in the same question is impulse. So we're going to do impulse again here. Obviously, we're going to use a different part of the equation. We've got the impulse. its value was 7.46 times 10 to the 3 Newton seconds. Don't use it in kilonewton seconds, use it in Newton seconds. And that's going to be equal to force times time. The time here is 2.10 times 10 to the negative 3 seconds. So we're going to take that, we're going to divide 7.46 by 2.10. We end up getting a force of what? What's that value work out to be? Colin? 3.55 times 10 to the 6, thank you. That's going to be in newtons. Now, how do we express that? Okay, this is a unit test or an exam. How do we express that? We're looking for the value of B. B is the base here. So the answer that we would express is simply 3.55. Does that make sense? It's not 3. It's not 4. It's not a one-digit answer. It's a three-digit answer. So it's 3.55. Now, another way that they could ask me to express this is A decimal B C times 10 to the D, and they're looking for the values of A, B, C, and D. If they ask me to express it that way, what's my answer? Three, 5, 5, 6. In that case, we wouldn't put in the decimal place. Does that make sense? Not only do we have to know how to get an answer, but we also have to know how to fill it in so that we get it marked correct when the machine scores it, right? Good at that? Just watched a video. We see this in movies all the time. Guy gets shot, gets propelled backwards by the bullet, the buckshot, through the window. Does this happen in real life? When a guy gets shot in front of a window, does he get propelled backwards through the store window? Is it realistic? Yes or no? Anybody want to take a stab at it? It's okay if you're... Not unless he falls backwards. I mean, he was propelled backwards in that scene, right? He wasn't just falling backwards. He was definitely being propelled backwards by the shot that had hit him, right? Is that realistic? Hey, Matt's saying no, not unless he just falls backwards. He's not going to be propelled backwards. Why not, Matt? Why is it not realistic? Why can he not be propelled backwards by the shot that hits him? Hey, maybe it hits him hard. Go ahead. No? Okay, the mass of the person is much greater than the mass of the shot. That's for sure. Yeah. The force of the shot would be transferred through a bigger area because he was wearing a vest. That's part of the idea behind a bulletproof vest, is it spreads that force over a much, much larger area, kind of like a football helmet or something like that, right? It spreads the force over a much larger area. But it's still ultimately acting on him, just spread out over not just a tiny little area, but a bigger area. In the end, did you see what happened to the guy that shot him? When he fired it, what happened to him? Shane, did you have a comment to make there? Okay. What happened to the guy that shot him? He fires the gun. Nothing happened to him. If Mel Gibson is going to be propelled backwards after he gets shot, then there must have been a lot of momentum in that shot that was transferred to him in order to give him enough momentum to go backwards through this glass. Would you agree with that? Where did the momentum of this shot come from? Well, the momentum before it was ever fired was zero. You can't get this much momentum on this shot going that way and then nothing going the other way. You can't create momentum. The idea is this. Before the shot was fired, there was zero momentum. The gun and the shot were one. They weren't moving effectively, so they had zero momentum. When the shot goes right, it has momentum to the right. In order to cancel that out, something's got to have momentum to the left. Well, if there was enough momentum in the shot to cause Mel Gibson to be propelled through the glass, then there must have been enough, or there at least should be enough momentum in the gun to cause the guy that's holding the gun to be propelled backwards as well. Does that make sense? In other words, if Mel Gibson's going to go backwards when he's hit by this shot because the shot has that much momentum, then the guy holding the gun has to be propelled backwards roughly an equal amount, because otherwise it would have been a creation of momentum, which can't happen. Now, is there a situation where he could conceivably be propelled backwards a little bit less than Mel Gibson or even a little bit more than Mel Gibson? You kind of alluded to it just a minute ago, whether you realize it or not. If the mass is different, right. If he's lighter than Mel Gibson, then he's going to be propelled backwards even more than Mel Gibson is. If he's heavier than Mel Gibson, then he's going to be propelled backwards, but a little bit less. Right? In the end, they both should theoretically have the same amount of momentum. Momentum to the right, momentum to the left have got to be equal. But the heavier guy experiencing the same momentum gain is going to be propelled backwards just a little bit less. Go ahead, Colin. No, I haven't seen that, no. This whole thing illustrates what we call the law of conservation of momentum. In the law of conservation of momentum, we say that in an isolated system, the momentum will always remain constant. In other words, it's always conserved. In other words, the momentum that we start with is going to be the momentum that we finish with. Now, what's an isolated system? That's kind of important here. What's an isolated system? It's a system in which neither energy or matter come in or out. If you've isolated a system so that no energy is coming in or out of the system from outside sources, and no matter is coming in or out of the system from outside sources, then the total amount of momentum in that system will always, every single time, stay the same. How does energy come into a system? What has to act on a system in order to get energy into the system, or for that matter, energy out of a system? No outside forces. If we've got outside forces that are acting on this system, then we're going to get energy coming in or out of the system, and then we're not going to have an isolated system. Okay, if we can isolate it from outside forces and matter coming in or out of the system, then as you say, the total amount of momentum will always remain the same. We're going to use this concept mathematically to analyze situations where we have collisions and explosions. By collision, I think that's fairly self-explanatory what a collision means. By an explosion, we don't necessarily mean literally a bomb blowing up. We mean basically one thing becomes more than one thing. When we fire a gun, the bullet and the gun were effectively one object until we fired it. When we fired it, the bullet goes one way and the gun goes back the other way. What's the total amount of momentum, by the way, in that bullet-gun combination before we fire it? 0. What's the total amount of momentum after we fire that bullet? 0. How is that possible? The bullet's going forward. If the bullet has 10 units of momentum going forward, what does a gun have? 10 units of momentum going backwards. What's 10 plus negative 10? 0. So the total amount of momentum would still be 0. Hey, I got a question for you then. If the gun goes back with the same amount of momentum as the bullet went forward, why does the gun not kill the person that fired it? Why does it not go just as fast and kill the person that fired the gun? Because the energy is spread out more? Not so much. Because the mass of the gun is so much greater than the mass of the bullet. If you've got a momentum of a bullet and the same momentum for a gun, the velocity of the bullet will be much, much higher because the mass is much, much lower. Does that make some sense? Of course, you also want to cradle that gun too, right? You don't want to put that gun, you don't want to hold that gun out. You want to cradle it against your shoulder so that basically your body's mass becomes part of the gun's mass so that that unit goes back even slower. The momentum is transferred to the gun and your body so that in the end you don't go back nearly as fast as the bullet goes forward. Finally, Of course, the total momentum in the system remains constant if we're isolating it from outside energy sources and outside mass sources. But the momentum of each individual object within the system can change. When you fire that gun, the momentum of the bullet increases. When you fire that gun, the momentum of the gun becomes a negative value. The momentum changes of each individual object within the system, but of the system itself, the momentum remains constant. How do we write this mathematically now? How do we write this as an equation? Well, if the total amount of momentum remains constant, before and after something happens, then we're going to say Pi is equal to Pf. The total initial momentum is equal to the total final momentum. Now, that's an equation that's not on your data sheet because it's more of a concept than an equation itself. Pi is equal to Pf. We'll wrap it up there for today, guys. We'll do the example problem with that tomorrow, and then we'll assign the homework that's associated with that tomorrow. Okay? So your homework tonight is quite simply the impulse worksheet, and of course you have a quiz on the mathematics of worksheet tomorrow, tomorrow, not including the graphs and not including the qualitative implications of it. Okay? Have a good night, everyone.